Hello everyone. Today's lecture and video will be about the first chapter in Signal and Systems course. So the outline of this chapter, first we will discuss the size of a signal, how we determine how strong is the signal, how loud is the signal. The second topic will be useful signal operation. So, for example, scaling the signal, making it longer, shorter, shifting the signal, delay, advance. And the third topic will be classification of signals. Is it continuous signal, discrete signals, causal, non-causal, periodic, non-periodic, and so forth. And the fourth topic will be signal models. We're going to learn about 3 or 4 models of a signal that we will be using a lot in this course, like exponential, sinusoidal, unit step, impulse. And the fifth topic will be classification of systems. Here we will classify, is the system digital system, discrete, continuous system, causal, non-causal, stable system, non-stable, and so forth. And the last topic will be, how do we model a system? Basically, how we describe a system by a mathematical equation, like a differential equation, that relate the input to the system and the output of the system. So let's start with the first topic, which is size of a signal. Now we will deal with 2 types of signals. One, we will call it energy signal, and usually energy signal, it exists over some interval and it eventually die out. So it could be a speed signal and then die out, or a temperature signal, and we call this energy signal. The second type of signal is power signal. That's a signal that looks like a periodic signal or a periodic signal, for example, like this, and it may last for a long period of time. Then we evaluate the strength of the signal by calculating the power here and the energy here. So to calculate the energy, the definition is this one for energy signal. And basically, this is the absolute value, just in case if the signal is a complex, then you have to find the magnitude first, then square it. In this course, most of the signal we will be dealing with are real signals, so we won't worry about the absolute value. Now, why do we need to square the signal? Well, if you don't square the signal and they ask you find the energy of this signal, basically the energy is just the integral, the area under the signal. And this area will be positive, this area will be negative, and integral, you just sum this area. Sometimes you will eventually get 0. But that doesn't make sense. The signal exists and I can hear it if it's speech signal. So we have to square it, so all signal will be positive and all area will be positive, and that's why we need to square the signal before we integrate. And then you take the integral and that will find the area, and the area will tell you the strength of the signal. Let's take this example. This is a signal, it looks exponential, exists t0 or higher. So if I try to draw it, it will look something like this. And at t equals 0, this equals 3. And this is the signal. So if I need to find the energy of this signal, how strong is it, I will calculate this integral. So let's start here, energy. Now the signal exists from 0 to infinity. So that will start from 0 and all the way to infinity here. And I square it, so that's 3e minus dt. And this equal. Now if I take the integral of this, it will be, and if I evaluate the integral, it will be, so the energy of the signal is just 9/4. And the unit, it will be depend on the nature of the signal, if it's speed signal or temperature, or, but for this course we will just call it joules. Now it's always a good idea after you calculate to look at the answer and reflect on it. For example, if I calculate, I may make mistake and the answer comes here negative. That doesn't make sense. Energy cannot be negative. It has to be positive. So it's always a good idea to go back to your solution and see where you made a mistake. Okay, so this is the energy signal. Now let's look at the power signal. Power signal is simply sinusoidal. So when we talk about the power signal, that means it repeats itself. So the first step is, if you look at a signal like this, you have to decide how big is you want to choose t, such that it like a period of the signal, then the signal will repeat itself every t. If it's a clear sinusoidal, just take one period. If it's statistically similar to a sinusoidal signal, then t capital may be large, so you cover all possible aspects of the signal. So after you make this decision, then the power is calculated as follow. This is similar to the energy. Basically, you take the signal, you square it, and you integrate over a full period from minus t to t over 2. And then you average it by dividing of t. One person may take t to be 1 hour, another one may take t to be 5 hours. So you divide by the average, so you will get, for the same signal, almost the same answer. And the limit t goes to infinity basically says the longer you make capital T the period, the more accurate is your answer. So let's solve this example. This is a pure sinusoidal signal. If I plot it, it looks like this. So if I want to calculate the power of this sinusoidal signal, it's p of x limit x of t is just a cosine, so that is now I can take the a square outside and express cosine square as half 1 plus cosine 2x. Use the trigonometric property. So this will be limit and finally now the integral of 1 is just t. The integral of this one is the area under the cosine function, and the area under the cosine is always going to be 0. The same thing, the area under the sine function is 0 because the positive area for the sine equal the negative area. For the cosine, the positive area equal the negative area. So the integral will always be 0. As long as you integrate over a full period or 2 period, 3 period. And if I evaluate this, I will get, now this t will cancel this and you get here. Now you don't have capital T in this term. So the limit has no influence. So the final answer will be a square over 2. And that's the power of a sinusoidal signal. And that's always the case. It doesn't matter what is the frequency of the cosine or if it's a sine. It's always going to be the amplitude squared divided by 2. And that's how we calculate the power of a power signal. All right, the next topic is we're going to learn about some useful signal operations that we will be using for signal processing. The first one is time delay, time scaling, and time reversal. And time delay, even in the human biological system, there is a big use of it. For example, let's say that's you listening to somebody speaking here. So his speech will reach both ears at the same time. Now imagine there is somebody else also speaking in the background. Now his speech will reach this ear before this ear. So there is a delay. So our auditory system will process this speech 1 and speech 2 and recognize that speech 1 reached both ears at the same time. While speech 2, there is delay in their arrival, so this person will realize, or his brain will realize, I am interested on this subject speech. So within few seconds, that speech will not be loud anymore. It will be like in the background, and you will be able to focus on this speech. In communication, when you see two antennas, they use this delay. And if you are searching for a specific word in a long conversation, you use the delay method to search for that word. So let's look at the delay. And here we always talk about signal in one dimension, which is time. This can apply also to a signal of 2 dimensions, like image. Now your variable is not time anymore, but it's a spatial in the x-axis and the y-axis. And the delay means you just move the object in the picture along x and y. So let's assume you have a signal x of t, which looks like this. And then I want to create a new signal. How related to x? It's just x of t minus tau. So it is a delay by that amount of time, tau. That could be 1 millisecond, 1 microsecond. So if I try to plot this signal, how is it gonna look? It's gonna look exactly the same but delayed. That means shifted to the right by this amount of time. So if this 0 reference like 12 noon, and this, for example, 10 o'clock in the morning, or just say -2 hours earlier than noon. And let's assume tau is 1 hour. So now my new signal, it's equal the old signal delayed by tau equal 1 hour. So it will start 1 hour late. For example, if I want to know what is the signal x at 3 o'clock, so I'm going to plug 3 here at t, minus tau is 1, so that's 2. So this new signal at 3 o'clock will equal the old signal at 2 o'clock. So if that is 2, then the new signal here at 3 o'clock will equal exactly the old signal at 2 o'clock. 3 minus 1, 2. So whatever that value here, that will be here. And this signal will look something like this. So when you have a minus, it means a delay. It means you shift the signal to the right. Now, advance by time, that means you advance the signal, then this will be plus, and you advance it by tau. So if I want to plot this signal, it will be exactly this signal, but shifted to the left by this amount here. Let's take an example for time delay. If you forget t minus 3, do I shift to the right and left? Basically just solve it mathematically and you will not go wrong. So for example, if I have this signal x of t, which is just a pulse of amplitude 2, exists from 1 to 4. Now if I want to find what is x of t minus 2, wherever I see t, I replace it by t minus 2. So this will be x of t minus 2 equal, there is no t here, so I just put 2, 1 bigger t, I replace it by t minus 2, 4. Now I want here to be just t, so I will add 2, but I have to add 2 here and here. So this will be t, and this will be 6, and this will be 3. Now if I plot this signal, it is 2 from 3 to 6. So that is 3, that is 6, and the signal equal to. So this is basically you shift the original signal 2 units to the right. If you try to do x of t plus 2, the same procedure, x of t plus 2. Here you subtract minus 2, and if you plot it, it is 2 from minus 1 to 2. So it is the signal shifted to the left 2 units. What if the signal is something like x of t, where t is from 0 to 3? So if you plot this signal, it will look something like this. Now x of t minus 2, wherever you find t, you replace it by t minus 2. And the same thing here, this will be 5, this will be add 2. And if I plot this signal, it's basically at t equal 2, 2 minus 2 is 0. At t 5, 5 minus 2 is 3. So I have these 2 points and I connect them, and this is the signal. And this is basically you shifted this original signal 2 units to the right, and you get this. Okay, let's do now time scaling. Now time scaling is compressing the signal or expanding the signal. And there are many applications in engineering for compressing and expansion. One application, I am sure you are aware of it and you heard it while you are driving in the car during advertisement for a product. The speaker will tell you all good things in a normal speed until the warning. Suddenly he's speaking very, very fast. That's compression. So he compresses the speech so it will be said in a small interval of time. Or an image, when you enlarge the image, that's scaling up, expansion. When you compress the image, that's compression. So in general, if you have a signal x of t and I want to generate a new signal such that it's x of at, where a is a constant, that means you are compressing the signal by a factor of a. If a is 2, you are compressing the signal by a factor of 2. If you are doing x of t over a, that you are expanding the signal by a factor of 2. For example, the new signal here is just x of 2t. So it is this signal compressed by a factor of 2. So this you divide it by 2, you get here. You divide this by 2, you get here, and this is the new signal, compressed by a factor of 2. Here, t over 2, you expand it by a factor of 2, and that will be your new signal. And you can plug mathematically to find, if you don't know, multiplying t by a constant, does it expand or compress? Just carry out the operation mathematically. For example, here, the old signal, if I want to find what is x of 2t. Again, wherever I see t, I replace it by 2t. So this is 2, and here I have 2t for 0. And I want this to be just t, so I divide by 2, so this will be t, and this will be 2, and this will be half. So the new signal will be, it's equal to from half to 2. So that is half, and that's 2, and the amplitude is 2. If I want to find x of t over 2, and 2 is a constant. If there is a t here, like t here, then you replace it by t over 2. But in our problem, it's just a constant. And then here, 1 and t, I replace it by t over 2, 4. Again, I need this to be t, so I multiply by 2. So I have here t, and this is 8, and this is 2. So if I plot it, it's equal to from time 2 to 8. And that's the signal. It's expanded by a factor of 2. The length here is 3. Now the length here is 6. This is half. The length here compressed by a factor of 2. So this is 1.5, the length. The next operation is time reversal. Basically, we rotate the signal around the y-axis. So if that is x of t, and I want to find the new signal is x of minus t, just I rotate this signal around the y-axis, so that will be this signal. If it was like this, if that was x of t, then x of minus t will be this. If that was 1, 5, this will be minus 1, minus 5. And we will see time reversal. There are many applications for it. One of it is when we do convolution between two signals. Convolution will require reversal of one of the signals. Now, there is a possibility where you may need to do two operations at the same time, like delay and compression. And that could be a little confusing, but if you follow the steps carefully, then you will be able to get the correct answer. For example, if I have this signal, and now I need to create this signal, x of 2t minus 6. So it looks like 2t mean compression by a factor of 2. Minus 6 mean there is a delay, but is it a delay by 6 units or is it a delay by 3 units? That could be a source of confusion. So the best way, I will carry the operation step by step. That means I will start with x of t and just keep going until I get to x of 2t minus 6. That means I will carry out many operations until I get to this mathematically. So let's start with, I need 2t. So I'm going to find x of 2t. And if I plot this is basically, we said it's a compression of a factor of 2. So if I plot it, it will look something. I divide this by 2, so that will be half. Divide this by 2, that will be 2. So I did the compression first. Now, how do I get to here? Well, that means just how did we get from here to here? I replace t by 2t. So now, to get from here to here, I have to replace t by something to give me this one. So if I replace t by t minus 3, then this will be x of 2t minus 2 times 3 minus 6, which is this one. Good. So what does it mean, t minus 3? That means you shift this signal by 3 units. So then I shift this signal by 3 units. That will be to the right. 3 plus half, that's 3 and half. 3 plus 2 is 5. And this signal is 2. This signal is 2. Sometimes students will make mistake and they get here and they said they get to here and they said to get to this point, I will just shift it 6 units. So this will be like 6 and a half and this will be 8. That's wrong. You have to follow the step. That means every time you replace t, and see what happens. Now, one other way to solve it is just write like the definition here. We said x of t equal 2t1 to 4. Now, if I want to find what is x of 2t minus 6, wherever I see t, I replace it by 2t minus 6. So this is just a constant, and here 2t minus 6, 4. I need this to be t. So I will add first 6 to every side. So that would be 2t, and this will be 10, and this will be 7. Again, I divide by 2. This will be t, this will be 5, and this will be 3.5. And if you plot it, it is from 3.5 to 5, and it's equal to. That's exactly the same as this one. Okay, now let's look at signal classification. Signal may be classified into first continuous time and discrete time signals, analog or digital signal, periodic or non-periodic, energy or power signal, we already discussed this before, deterministic or probabilistic signals, causal, non-causal signal, even and odd signal. So let's go through them one by one. First, when we say continuous versus discrete, here we are talking about time. Is the time continuous or is the time discrete? We are not talking about the amplitude. The amplitude here is continuous. For example, this signal is a continuous time because for every single possible value of time, there is value of the signal. Now, this signal is discrete because the signal only exists on a specific interval of time. It could be 1 second, 2 seconds. There is no value between them, 1.5. And then we say this is continuous signal, this is discrete signal. Now, analog versus digital signal, that means it's discrete on the time domain and also the amplitude, has only possible values, either 0 or 1. So when I say analog, continuous, that means the time is continuous. Analog, that means the amplitude has all possible values here. When we say analog discrete, that means the signal is discrete in the time domain, but the amplitude can have any value. Now, when we say digital, that means the amplitude will have only two possible values. Continuous means the time is continuous, which is like this. So the amplitude could be 5 volt minus 5 volt, or 1 minus 1, or 0, 1. And when we say digital and discrete, then that will be the signal. It's discrete in the time domain, only this possibility, and the value of the amplitude has only two possible values, 1, 0, or 1 minus 1. Now, when we say periodic versus aperiodic, if the signal repeats itself every time interval, then that's a periodic signal. For example, this one. This is a periodic. The signal repeats itself every t0. And the mathematical condition for a signal to be a periodic is the following. That means the signal x of t always equal the signal x of t plus a specific value. For example, the signal here, the value here, if I go one full period, same value. If I go another full period, same value, the signal. Then that's a periodic signal. Now, deterministic versus random. Deterministic signal means I can predict what the signal will be at any specific time. Basically, if you can express the signal mathematically, then that's a deterministic signal because I can plug a value for time, t, and calculate what the signal amplitude will be. Then we say this is a deterministic signal. A random signal, that is something you cannot predict, something that looks like this. So if I ask you, if you have been looking at the signal for like 2 seconds, can you tell me what will the signal be the next 5 seconds? You won't be able. But sometimes we say statistical deterministic. That means it's not perfect periodic, but there is a pattern that I can predict what the signal will be. Like in speech, when you say the vowel O, E, this looks periodic. And statistically, I can, with some accuracy, predict what will be the signal in the next 1 millisecond, 2 milliseconds. A random signal, that is a signal you cannot tell. If you watch the signal for 10 minutes, you cannot predict what the future samples will be. Then it's a random signal. The next characteristic of a signal is causal versus non-causal signal. And this is basically a signal that starts at t equals 0 and after we call it a causal signal. A signal that has a past value and future value, then we call it non-causal signal. So whenever x of t exists for t equal or larger than 0, that's causal signal. Signal that exists for negative value of t, non-causal signal. Another characteristic of a signal is even and odd function. And sometimes mathematically or signal processing is much easier for even function, and sometimes it's easier for odd function. So I can express any signal to be a combination of even and odd signals. But for now, let's just define what do we mean by even signal. First, we determine the vertical axis. Then this basically says if the signal is even, then x of e of t will equal x of e minus t. So that means the value of the signal at time equal 1 will equal the value of the signal at time minus 1. So if that is 1 and this is minus 1, then this value are the same. At 2, this value will be the same. Then this is an even function. A cosine function is an even function, because if you plot a cosine function, looks like this. That's an even function. Now an odd function is determined by this equation, which basically says the value of the function at t equal negative the value of this function at t minus. So if this is the function, if a is 1, if that's the value, then x0 minus 1 will be negative of this value, which is here. So if that was 3, then this will be minus 3. And a sine wave is odd function. If I draw a sine wave, looks like this. So if I have a time here, then if that, for example, like 0.1, this will be minus 0.1. So that's the definition of even function and odd function. Now, if in signal processing you multiply even function time an odd function, the product will give you an odd function. If you have an odd function time odd function, the product will be even. And if you have even function time even, you will have even function. Now, as I said before, sometimes some signal processing is much easier done on even signal or odd signals. So if I have a signal that is not even, not odd, something like this, I can express this signal as a combination of even function and odd function. So you have the signal x of t. If I take this signal, let's make a plot and show you. Let's say this is x of t. So this is not even, not odd. So if I create this, which is basically x of t with itself inverted, and let's say this is 4, so then this will be something like this. This is the original signal, x of t times half, so that's 2. And I add to it the inverted, which is here. Say this is 2. So now this is even. And if I add to it this component, which consists of x of t times half, so it's this 1 times half, which is this, 4 become half, minus x of minus t. So this is x of minus t, and I multiplied by minus, so I'm inverting it. So it will look something like around the horizontal axis. So this is x of minus t, this is x of t half. So now if I look at this signal, that's an odd signal. If I add these two signals, I will get back this signal. If I add this and this part will cancel this part, and this part will add with this, and I will get the original signal. So I have a signal x of t that was not even, not odd, and I express it as a linear sum of even function with odd using these mathematical equations. Okay, this example is just similar to this example. You can read it and look at it. Okay, the next topic is signal models. So we're gonna learn about 4 signals that we will be using extensively in this course. The first signal is unit step function, pulse signal, unit impulse function, and exponential function. Let's review them. So basically, unit step function, it's equal 1 at t equals 0 or larger, and before that it's 0. So you can think of a unit step function as if it's a switch. You turn on the system at t equals 0. That t equals 0 could be 12 noon or 12 midnight. And you turn it on, then the output is 1. The output will start. So that's how we use the unit step function, is to determine when the signal starts. For example, if I have this exponential signal, if I say x of t equal e minus a of t, and I ask you to plot it, it will look something like this, because here I didn't specify where does the signal start exist. So you will assume from minus infinity, which is going to be way infinity, something like this. And here it's 1. At t equals 0, it's 1. But if I tell you this is x of t equal e minus a of t u of t, that's the unit step. That means this signal only exists from 0 to infinity. Now if you plot it, this part doesn't exist. So it starts from t equals 0, which is 1, and just keep going until t infinity. And that's one use of u of t, to determine when the signal exists. Now a pulse signal, this is the simple, it looks like pi, t over tau. Now the denominator of t is tau. That tau, it tells you the width of the pulse. And it is centered around 0, the pulse. Unless if this t is something like t minus 3, that means you shift it 3 units. So it will be centered around 3. But right now you can think of this t as if it's t minus 0. So it's centered around 0. And the amplitude here, if I'm not writing anything, that means the amplitude is 1. So that is the symbol for pulse of width tau, centered around t equals 0, and that's the plot. Now if I want to express this pulse in terms of a unit step functions, I can express it in terms of this pulse. So this is a pulse of high 1, which is this, width is 2, and it's centered around 3, so that's t minus 3. I also can express this pulse in terms of u of t. So this pulse, if I add this unit step function, which is u of t shifted 2 units to the right, or delay, so that's u of t minus 2. And this pulse is u of t shifted 4 units to the right, but the amplitude is minus 1, so that's minus 1. Now if I add these 2 here, this is 1 will stay until 4, then 1, and you subtract from it 1 is 0. So you end up with this pulse, which is this. So I can express any pulse in terms of a unit step function. If I have this pulse, this will consist of a unit step function shifted to the left by 1 unit, so that will be this, all the way to 4, plus a unit step function shifted, or I can say instead of plus and minus, if I have another unit step function shifted to the right by 4, it starts here. Now if I subtract these from here, u of t plus 1 minus u of t minus 4, then I will end up 1 until 4 minus 0 is just 1. Now 1 minus 1 is 0. So this is basically u of t plus 1 minus u of t minus 4. All right, the next important function is the unit impulse function, and we call it delta t. And delta t equal infinity at t equals 0 and equals 0 everywhere, but the area equal 1. And anywhere it's 0. And in real life, this impulse, which looks like this, you can think of it, if you create it using gates and flip-flop, it's basically, it gives you a pulse, a voltage for 1 nanosecond. So this width become very small until it's almost 0. Then the area here is always 1. So as the width becomes 0, the height becomes very large. And we represent it by this 1. And the area of the impulse is equal 1. And if I have a unit step function, the relationship between unit step function and an impulse, that's a unit step function. Now if I take the derivative in this region, this doesn't change, so the derivative is just 0. Same thing here, in this region u of t is just constant 1, so the derivative is just variation. The derivative is a measure of the variation of the signal. So here the derivative is 0. Here in this region also the derivative is 0. But what happened here in this instant of time? Suddenly the signal changed from 0 in a very short period of time to 1, so the derivative will be very large. The rate of change is very large, and we represent it by a delta function, and that's the derivative of a unit step function is just a delta function here. So this is the relationship. This you should have it in your formula sheet. The integral of a delta function is 1. A derivative of a unit step function is just an impulse, and we use this impulse in many signal processing. Basically, one important application is sampling, when we sample a continuous signal to convert it to a discrete and digital signal. So what happened when you multiply any function by a delta or by an impulse? So if I have a signal here, delta t, that may look something like this, phi t, and I multiply it by a delta, which is here. What is the product? The product, you will get again an impulse, but the amplitude of the impulse will be the value of this function at t equals 0, which is this. So the value of this function at t equals 0 times a delta function. Some students make mistake. They write the answer this way. Now this is wrong. If you don't include the delta, this is wrong. Why? Because here you are basically saying the output is whatever this. This could be 3. Is 3. 3 what? 3 for a long time, 3 volt for like infinite time, 3 volt for a short time. So you have to indicate this is just 3 for that instant of time. That means at t equals 0. So make sure you always include the delta after you do the product. Now, if I told you what is the value of this function times t minus 4, delta t, well, where is this delta function located? It's located at t equal 4. Basically t minus 4 equals 0, so that's t equal 4. Or it's just a delta shifted 4 units. So that will be here. So if I do the product, then the answer will be the value of the function phi at 4, the location here. So this value times the delta function t minus 4. And this is these equations. So a function multiplied by a delta located at capital T is the value of the function at this capital T times the delta function or the impulse. Okay, I said we use the impulse in sampling a signal. So first we learned how we do multiplication. Now what happened if I do the multiplication then integration? What's the answer going to be? So let's do this process. So minus infinity to infinity. When I multiply these two, what do I get? I get this. Now this is a constant. It doesn't have t anymore, this variable. So I can take it outside the integral. Now this integral, as we said before, the area under a delta function is 1. So this is just times 1, and that's the answer. So if you have a function multiplied by a delta located at capital T and then you integrate, it's the value of this function at this location. It's just a number. And that's how we use, if you have a continuous signal, we sample it by multiply it by a train of impulses. And that train of impulses will preserve the value of the function at these locations. And when we learn sampling theorem, we will go back to this property. Now I can multiply a signal by a delta in the time domain, or I can multiply it in the frequency domain, like this one. It's in the frequency domain, so it doesn't matter. So here you have a function multiplied by a delta function located at 3. It could be 3 hertz or radian per second. So what is the answer? Wherever you see omega, you replace it by minus 3, because this impulse located here. So then this will be 1j3 plus 2, and don't forget including the impulse. That has a magnitude and phase, and it's located at this location. Now, if I evaluate these, again, first I will do the multiplication, then the integration. Well, I am evaluating this function at t equal minus 3. So that will be at delta t plus 3 e minus 3. Now, this has nothing with time, so I can take it out. And now the area of this one is 1. And that's the answer. Now, sometimes I will give this in the quiz and ask the student what's the answer, or make it like 0 here. And the student will automatically will say 1. That's wrong. Why? Where is that impulse located? It's located at minus 3. Where am I integrating? I'm integrating in this interval from 0 to infinity. So there is nothing here. And you're integrating 0. So the answer, not 1. It should be 0. Because that impulse is outside the range of integration. So always look and make sense of the mathematical equations before you rush into writing the answers. Okay, let's look at this example. So here we want to find the derivative of this function. So one way is, let's plot this function. So if I plot it, it consists of a unit step function shifted 2 units, and the amplitude is 1. If I plot this, it's a unit step function started at 4 with amplitude -3. If I add these, I will get this. 2 to 4, it's 1 minus 0. And from 4 to infinity, it's minus 3 plus 1, so that's minus 2. And if I take the derivative now of this function, so if this is x of t, now if I take the derivative and plot it, well, this is 0, so that there's no change, so the rate of change is just 0 until 2. Then there is a sudden change up 1 unit, so that's an impulse, indicate a rapid change or a quick change. And then here it stay 1, no change, just a constant, so that's 0 until 4. Then there is a sudden change downward. How many units? That's 1, and this is 2, that's 3 units downward, so that would be an impulse 3. So the answer is just an impulse at location 2 of 1, and another impulse of amplitude 3, minus 3, located at 4, minus 4, and that's the answer. So dx dt equal delta t minus 2 minus 3 delta t minus 4. And you can do it mathematically. Unit step is a delta function. The derivative of unit step is a delta function located at 2, which is this. The derivative of this unit step function is minus 3 located at 4, which is this. Okay, another important function is the exponential function. And you are familiar with it. We're always familiar with e minus 3t, or e, that's decay exponential, e 4t, that's growth exponential. And this is the general form. But here s now can be real, like in these cases, or can be complex, like 3 plus j4. And later on, when we do the Laplace transform, that s will always be complex, and it represents frequency. It has magnitude and phase. So depend on the value of s, the plot will be different. In general, s we will represent it as a complex variable or complex frequency. It has sigma, which is the real part, and j omega, which is the imaginary part. Sigma, the real part, it tells the decay rate. So it's frequency rate, but it tells you how fast does it decay or how fast does it grow. J omega, it tells you the rate of oscillation. Is it 1,000 hertz, 10,000 hertz? So that is usually the value of s. it represents complex frequency. So if I have Es of t and I express S as sigma and j omega, now I can break these to E sigma t times E j omega t. Now I can use trigonometric property and express these as cosine omega t, j sine omega t. Now you may wonder, okay, but in real life we can't have imaginary signal. So this is j, so how do you create that in the lab? We only have real signal. I can create these in the lab, but with the j is a problem. But if I want to generate a real signal from Es of t, let's create another one, which is a conjugate. So that means S conjugate, you just change the sign of the imaginary part to minus. So that will be this one. Now if I multiply, I get this and this one. Again, I use trigonometric property to express the E minus j omega t is this. Now if I add these two and multiply by half, well, these will cancel here, and you will get these plus these, two of them. You multiply by half, you get one of them. Now that's a real signal. That's a signal we can build in the lab. And it depends on sigma and omega. I can generate all kind of signals. Let's look at the next slide. Depending on the value of sigma and omega, you can have different shape of the signal. For example, if I choose S just to be 0, sigma plus j omega, sigma is 0, omega is 0, then I just a constant, k. So that's a DC. So I can express a DC voltage as of 3 volt as just like this, where S is 0. That means a DC voltage doesn't oscillate, omega is 0, it doesn't decay, sigma is 0. If I want to just generate exponential signal, then omega I make it 0. Doesn't oscillate, it's just exponential, either decay or grow. So then I get just sigma. If sigma is negative like -2, then it decay rate. If sigma is positive like 3, then it grow. Now if I want to generate just pure sinusoidal signal, I can add these two and I get these just like what we did here. Now if I set sigma to be 0, that means there is no decay or growth, then I just get cosine omega t. And that's just a pure sinusoidal with oscillation rate equal omega. See, from that exponential function, we can create a DC, we can create exponential, grow or decay, we can create pure sinusoidal. We can create a sinusoidal with decay or growth, like the next slide here. Examples. Here S equals sigma plus j omega. In this plot, omega is 0. But if sigma is positive, then it's growth. If sigma is negative, then it's a decay. If sigma is 0, then just a pure DC. Now here, for this one, if I make sigma 0, then I just get a sinusoidal with oscillation rate omega. So that's a pure sinusoidal here. Now this one, sigma is less than 0 and omega has some value. So omega will determine this oscillation rate and sigma will determine the decay rate here. How fast does it go to 0? We know that omega is radians per second or just 2 pi f. And f is the oscillation rate, 10 cycle per second. And f also equal 1 over t, where t is the period. So if I take this peak here and this peak here, that's the period. And the reciprocal of t will give me the frequency, how many cycles per second. Now in this plot, sigma is larger than 0. So that's exponential growth. And omega could be any value. So that will be this signal. And we will be using these exponential a lot. So get familiar with it for a different value of S, which is sigma plus j omega. This will end this video. And next video, we will talk about system and classification of a system. Thank you.